So we are going to look at powers of primitive roots and determine exactly how many primitive roots does any prime number have. To do that, let's take a look at some number g that is a primitive root mod p. In other words, the order of g mod p is equal to p minus 1. One of the consequences of that, by the definition of the order, is that g to the p minus 1 is congruent to 1 mod p. That might be obvious by Fermat's little theorem, but we can derive one important consequence from this, which is, if g to the p minus 1 is congruent to 1, importantly, it's not congruent to 0, which means that g is not a multiple of p. And since p is a prime number, that means that g has to be co-prime to p. So they share no prime factors. Now let's take a look at the powers of the primitive root g. So we're looking at the numbers g, g squared, g cubed, g to the fourth, and so on, all the way up to g to the power of p minus 1. The first result we're going to prove here is that all of these numbers are incongruent mod p. In order to do that, let's suppose we have two numbers in this set, g to the k and g to the m. And let's suppose, for contradiction, that they were congruent mod p. Now we're not counting the case where k is equal to m because of course any number is equal to itself. So we know that k is not equal to m. And let's say that m is greater than k. If k were greater than m, it would be the same thing, we just flip the congruence. In that case, we know that we can write m as k plus some positive integer remainder r. So r is the difference between m and k. We can substitute k plus r into this congruence right here. So we have g to the k is congruent to g to the m is g to the k plus r, which we can write as g to the k times g to the r. Now, we know that g is co-prime to p, and that means that g to the k is also co-prime to p. It still has none of those factors of p. And therefore, by one of the cancellation rules in modular arithmetic, we know that we can cancel these two, and that's going to leave us with 1 is congruent to g to the r mod p. Is this allowed? Well, we know that we picked m and k out of this set. M and k are all numbers between 1 and p minus 1. If we take the difference of two numbers that are between 1 and p minus 1, that difference is always going to be less than p minus 1. There's no way for us to get p minus 1 out of that difference, because the biggest possible difference is p minus 1, which is p minus 2. What that's telling us is that r, because r is the difference between m and k, we know that r is less than p minus 1. If g to the r is congruent to 1, and r is less than p minus 1, then we've found a number where g to that power is congruent to 1 that isn't p minus 1, but that would mean g isn't a primitive root, because the definition of a primitive root says p minus 1 has to be the smallest possible value. What that's telling us is that this congruence right here has to be false. There's no way for two numbers in this set to be congruent mod p. So this is what we would call a complete set of residues mod p except for 0. So all of these numbers are incongruent mod p. In fact, we can actually show that this is a biconditional. In other words, we just showed that if g is a primitive root mod p, then all of these numbers have to be incongruent. What we're going to show now is that if all of these powers of g are incongruent, that proves that g is a primitive root mod p. To see that that's true, let's start with Fermat's little theorem, which says that g to the p minus 1 is congruent to 1 mod p. We know that this is true because if g were a multiple of p, then these would not all be incongruent because they'd all be 0 mod p. That means that g is not a multiple of p, so Fermat's little theorem applies. On the other hand, we know that none of the numbers in here are congruent to g to the p minus 1, because our initial assumption was that they were incongruent. That means that there's no other number in here, g to the k, that's congruent to 1 mod p, for k less than p minus 1. But these two statements together are the definition of a primitive root. What this is saying is that p minus 1 is the least positive exponent where g to that power is congruent to 1 mod p. And therefore we've shown that if all of these numbers are incongruent, then g has to be a primitive root mod p. Essentially, this is an alternate definition for g being a primitive root mod p. The alternate definition says when we raise g to the powers between 1 and p minus 1, those all give us different results, mod p. Now there's another property of primitive roots that makes them very, very interesting, and that is how congruence of their exponents is related to congruence of the numbers themselves. So let's take a look at what that means. Suppose we have two numbers, a and b, where g to the a is congruent to g to the b mod p. So this is similar to what we were looking at before, but in this case a and b can be any integers we want. They don't necessarily need to be from that set. If this is true, like before, we can write a as b plus some remainder that's the difference between a and b. So that means that g to the b times g to the r is congruent to g to the b mod p. Like before, we know g to the b is co-prime, so we can cancel that out. We get g to the r is congruent to 1 mod p, and that means because g is a primitive root, this is only possible if r is a multiple of p minus 1. The important thing to notice here is that each of the steps that we just went through are reversible, meaning that they work in the opposite direction. From this first fact, we can conclude g to the r is congruent to 1. We can multiply by g to the b on both sides, and then we get this result over here. Now let's remember how we defined the number r. We defined r to be the number such that a equals b plus r. If we subtract b on both sides, we see that r is equal to a minus b. So this last equation is telling us that a minus b has to be some multiple of p minus 1. Notice that this is actually the definition of a congruence mod p minus 1. This is the same thing as saying a is congruent to b mod p minus 1. The difference, a minus b, is a multiple of p minus 1. Remember that we said before that this statement down here, r is a multiple of p minus 1, that is biconditional, because all these steps go backwards as well, with this statement up here. G to the a is congruent to g to the b mod p. Because we can do these steps in either direction, these two statements are exactly equivalent. If a is congruent to b mod p minus 1, then g to the a is congruent to g to the b mod p, and vice versa. What that's telling us is that the congruence of the powers of two primitive roots, mod p, is the same thing as talking about the congruence of their exponents, mod p minus 1. And that's going to be a super important property. We'll see why in a second. So besides the fact that the congruence of powers of primitive roots is related to congruence of the exponents, that's just a really cool idea. It's also going to be useful. Let's consider the set 1, 2, 3, up to p minus 1. What we're going to do is construct a new set using the elements of this set. Suppose we have some number n, which is co-prime to p minus 1. We're going to multiply all the elements in this first set by n. And that's going to give us a new set which we'll call S, and that set contains n, 2n, 3n, and so on to p minus 1 times n. Let's think about the elements of S here. We know that n is co-prime to p minus 1. What that tells us is that if we're working mod p minus 1, multiplying by n is an injection. If we look at the numbers in this first set, they are all incongruent mod p minus 1. So if we multiply by n, which is an injection, all the numbers down here are also incongruent mod p minus 1. What if we think about the numbers in each of these sets, not just as numbers themselves, but as exponents of primitive roots? Up here, we're looking at g, g squared, g cubed, and so on, up to g to the p minus 1, like we see over here. In this set S, we can consider all of these numbers as powers of a primitive root, like this. First, we're looking at g to the n. Then we're looking at g to the 2n, which we'll call g to the n squared. Then we're looking at g to the n cubed, and so on. But notice that each of these numbers we're saying is an exponent of the primitive root. One of the results that we proved a minute ago is that if the exponents are congruent mod p minus 1, then the powers of the primitive roots will be congruent mod p. And we can also say the opposite. In other words, because all of these numbers are not congruent mod p minus 1, all of these powers of g to the n will be incongruent mod p. And one of the things that we proved at the beginning of this video is that if we have a number where all of the powers between 1 and p minus 1 are incongruent mod p, then that number has to be a primitive root, meaning g to the n is also a primitive root. When we multiply by n, it's an injection, so all of these exponents are incongruent mod p minus 1, so all of these numbers are incongruent mod p, which means g to the n is a primitive root. Now the condition for that being true is that n is coprime to p minus 1. So what we can say is that if n is coprime to p minus 1, then g to the n is also a primitive root mod p. Now we're going to look at one more result before we get to the final punchline, which is showing how many primitive roots there are mod p. Instead of looking at a number n, which is coprime to p minus 1, we're going to look at a number that is not coprime. So suppose we have some number n where the greatest common divisor of n with p minus 1 is greater than 1. In that case, let's call the greatest common divisor of n and p minus 1 x. So we know that x is greater than 1. One of the properties of the fact that x is a common divisor of n and p minus 1 is that we know p minus 1 over x and n over x are integers. So since x is a common divisor of both of these numbers, when we divide by x, these are both whole numbers. Now let's consider the number g to the n to the power of p minus 1 over x. We know by exponent rules that we can move around the numbers in this exponent as follows. We can write it as g to the n over x, and then to the power of p minus 1. Now we know that n over x is an integer, which means we're taking g to some integer power, so this inside is a whole number, and we're raising it to the p minus 1. By Fermat's little theorem, we know that this has to be congruent to 1 mod p. But something is a little bit fishy with what we got right here. We're trying to look at whether g to the power of n is a primitive root. But what we just showed is that there is some number, p minus 1 over x, where if we take g to the n and raise it to that power, the result is congruent to 1 mod p. If g to the n is a primitive root, then the only number that should have that property is p minus 1 and multiples of p minus 1. But x is bigger than 1, which means that p minus 1 over x has to be less than p minus 1, which means we've just shown there's a number less than p minus 1, where if we take g to the n and raise it to that power, we get 1 mod p. That's not allowed for primitive roots, which means that g to the n is not a primitive root. So what we've just shown is that if g is a primitive root mod p, then for numbers n that are coprime to p minus 1, g to the n is also a primitive root. For numbers n that are not coprime to p minus 1, g to the n is not a primitive root. But additionally, we know that all these numbers, g, g squared, g cubed, and so on, are incongruent, which means that these numbers comprise all of the numbers mod p except for 0. And of course 0 isn't a primitive root because 0 to any power is not 1. So what that means is these are all of the possible numbers mod p. So if we have one primitive root g, then for any other primitive root, any other possible primitive root, we can represent it as a power of g. So all of the primitive roots mod p are contained in this set. All primitive roots mod p are some power of g. So if the only powers of g that are primitive roots are the ones where the power is coprime to p minus 1, then those comprise every single possible primitive root. In other words, the set of primitive roots mod p is the set of powers of g that are coprime to p minus 1. How many are those? Well, that's going to be the number of integers coprime to p minus 1, the totient function of p minus 1. So we've shown that the number of primitive roots mod p is phi of p minus 1. And we've also shown that we only have to get one primitive root directly. As soon as we have one primitive root mod p, all we have to do is find the numbers coprime to p minus 1. And then g raised to those powers, that's going to give us every single primitive root mod p.